All right, today guys, we are going to introduce you to a new function called the polynomial function. Now, specifically, you guys have seen polynomial function in an algebraic sense. Today, we're going to be looking at polynomials more in a graphical sense and throughout this first section here of this particular unit. So let's get started. It says, I can determine the end behavior of a polynomial function if a polynomial function is even or odd and use this information to help me sketch a graph. So that's the objective, okay? So 1, know end behavior. 2, can you use that end behavior to sketch your own graph, okay? It says the graph of a polynomial function is blank, meaning it can be drawn without lifting the pencil off of your page. That would be continuous. Okay, so there are no breaks in the graph. If you think about the functions that we've dealt with, leading up to this, more specifically, the one we just did in the last unit was rational functions, right? And a rational function did have breaks in the graph in asymptotes and holes, right? Those are discontinuities, right? So that function was not continuous. You do not have that when it comes to a polynomial. And behavior refers to the direction the arrows are pointing at the start and at the end of the graph. Even degree function. So even degree, remember, we know that degree is the leading or the biggest exponent of that particular polynomial. So an even degree function would be a degree that is even. Okay, so for example, if you had x to the fourth plus x squared minus 3, right, that would be an even degree polynomial because the highest exponent is the degree, and that degree happens to be even, okay? Now, the next thing, it says the leading coefficient is positive. So in this case, obviously, the leading coefficient here is positive. All right, so what I would like you to do now, guys, is think about a specific polynomial that you've dealt with for a long time, and that happens to be a quadratic, right? So a quadratic function is a polynomial, but specifically it is a quadratic. And the reason it's quadratic is because the highest degree is 2. But do you guys agree, inside of a quadratic, so if I had a quadratic that's x squared plus x plus 1, whatever the case may be, right? The highest degree here is 2, and is that degree even? Yes, it is. And what do you know about the graph of a quadratic? It's a parabola, right? And both ends of a parabola are going in the same direction, aren't they? Right? And in this case, both ends are going up, right? Because the leading coefficient is positive, okay? And we said that for any even degree polynomial, since you guys have been dealing with one since you were a freshman in high school, right? It just happened to be a quadratic, right? Now we're talking about any polynomial that has an even degree. The end behavior of a quadratic or a parabola, both ends are going up, correct? Right? So let's talk about this. As x approaches infinity, so as x approaches infinity this way, right? As x keeps getting bigger and bigger and bigger, where is the y value approaching? Well, it looks like the y value is approaching infinity as well, right? And that should make sense, right? As x keeps getting bigger, y is getting bigger, right? Because 2 squared is 4, 4 squared is 16, so on and so forth. And just think, if you weren't to square it, you were to take it to the 4th power, it's getting bigger even faster, right? So that should make sense, all right? As x gets negative, so as x is getting smaller and smaller and smaller, where is y going? It's still going in the positive direction. So as x is getting more negative or smaller and smaller and smaller, it looks like y is getting bigger and bigger and bigger. And that should still make sense because negative 2 squared is a positive 4. Negative 4 squared is a positive 16. Okay, does that make sense? All right. So it doesn't matter how big the degree of the function is. If it's even, you know that both ends are going to go up if it has a positive leading coefficient. Okay? All right, well, let's talk about a an odd degree function then? So just like an even degree, we said that you guys have dealt with that for the majority of your high school career. You've dealt with an odd degree function for the majority of your high school and middle school career. And that odd degree function happens to be a line, right? So if you think about a line, that would be like x, x plus 3, correct? Y equals x plus 3. The degree here would be 1, right? Degree is the highest exponent. The highest exponent here is 1. And that 1 happens to be odd, yes? Do you guys all agree with me there? Okay. So let's think about that. If we were to graph a line that has a positive leading coefficient, do you guys agree that the right end would be going up and the left end would be going down, right? Does that make sense? And you think about that, if I were to draw in that line, per se, that is a positively sloped line, yes? Right? Well, guess what? An odd degree function that has a positive leading coefficient is going to have the same end behavior. And that should make sense because a linear function is a polynomial, right? It's specifically a linear function. Does that make sense? So now we're just going to expand our knowledge of polynomials and give you functions that have odd degrees that are bigger than 1 now. But the end behavior does not change. Does that make sense? So as x is getting bigger and bigger as it is approaching infinity, where is y going? It's going towards infinity as well. So as x approaches infinity, y approaches positive infinity. Make sense? Okay? And then as x, let me use a different color here. As x approaches negative infinity, where's my y value going? Oh, it's going down, yes? Right? So for any odd degree polynomial with a positive leading coefficient, as x approaches negative infinity, my y value is approaching negative infinity as well. As for the domain and range, think about a line, right? The domain of a line is negative infinity to infinity, right? It is continuous throughout. The range is also negative infinity to infinity. All right? All right, let's sneak back to even degree function, only this time with a negative leading coefficient. So let's think back to the quadratics that we were talking about, right? So if you had something to the effect of x squared plus x plus 1, right? Let's just say. But instead of a positive leading coefficient, we made this thing a negative leading coefficient. Well, what do you know about a parabola, right, that has a negative leading coefficient? Both ends, or the parabola is facing down, correct? Right? Does that make sense? And that's the same thing that happens for any polynomial. It doesn't matter the degree. As long as it's even and it has a negative leading coefficient, both ends are going to be facing down, like what would be the case with a parabola. Does that make sense? Just the thing in the middle is going to change if it's not a quadratic. That make sense? All right, so, and behavior again. As the x value is getting bigger and bigger and bigger, as we keep getting farther and farther on the x, what's happening to the y? It's going down, right? So as x goes towards positive infinity, my y value is approaching negative infinity, right? Okay. Other side. As the x value keeps getting smaller and smaller and smaller and smaller, where is my y value going? It's going down. So as x approaches negative infinity, y is approaching negative infinity. So what can you say about the end behavior of an even degree polynomial? Both ends are going in the same direction, right? If it's a positive, both ends are going up. If it's a negative, both ends are going down. And I would strongly suggest, guys, that you use the example of a quadratic to help you, okay? If the degree is 4, 6, or 8, the function is not going to be a parabola, but the end behavior, the things that are happening at the end, are going to take on the same direction. As for an odd degree function with a negative leading coefficient, we are still going to do the same thing and discuss and talk about what happens to an odd degree function with a negative leading coefficient in terms of a line, correct? Because that's the most common odd degree polynomial function you guys have dealt with in your mathematical career. So if you had something like y equals negative x plus 3, okay, we agree that the degree here is odd because the highest exponent is 1, and 1 is an odd number. We also agree that the leading coefficient here is negative. Well, if that's the case, guys, what do you know about a negatively sloped line? The right end is down, and the left end is up, correct? Right? Do you guys agree that that would be a negatively sloped line, yes? Well, the ends of the graph take on the same direction, even though the polynomial is going to have a higher degree than 1. Does that make sense? It would just be an odd degree, 3, 5, 7, 9, whatever the case may be. Okay, so the ends are still going to be the same. It's just what's in the middle that changes. Okay, so let's talk about the end behavior of an odd degree function with a negative leading coefficient. So as the x value gets more positive and we approach infinity, where is my y value going? It's going towards negative infinity. So as x approaches positive infinity, my y value approaches negative infinity. Okay? And as x gets farther and farther and farther to the left, right, or it gets farther and farther negative, what's happening to my y value? It's getting bigger and bigger and bigger. So as x approaches negative infinity, my y value is approaching positive infinity, okay? And then the domain and range for this, obviously, since this is a continuous function, would be negative infinity to infinity for the domain and negative infinity to infinity for the range. All right, so let's look at some examples here. Example number 1, we have a polynomial here with a negative leading coefficient and an odd degree, right? So what do you know about an odd degree polynomial? We are going to compare that to a line, correct? Right? And what do you know about a negatively sloped line? The left end is up and the right end is down, correct? Right? So if we were thinking about end behavior, as the x value goes towards infinity, where's the y value going? It's going down, correct? So that'd be y approaches negative infinity. And what do we know about the negative x? So as x approaches negative infinity, where's the y value going? It's going up, correct? So as x approaches negative infinity, my y value approaches positive infinity, okay? And then it says state the domain and range. Well, what do we know? For an odd degree polynomial, we said it's like a line, correct? So the domain would be negative infinity to infinity. The range would be negative infinity to infinity. Example 2. Let's look. We have a positive leading coefficient now, and we still have an odd degree polynomial, yes? So we're going to relate it to a line again. And what do you know? A positively sloped line, the left end is going down, the right end is going up, right? Okay, again, the reason I put dashed lines in here is because if it's a polynomial, there's going to be different things happening in the middle, but the ends are going to be the same. Okay, so end behavior. As my x value gets more and more positive, what's happening to my y value? It's going up, correct? So as x goes towards positive infinity, my y value goes towards positive infinity. As x gets more and more negative, what's happening to my y value? It's going down, correct? Right? So my x value goes towards negative infinity. My y value is going towards negative infinity. Okay? And then as for the domain and range, again, domain, Since it's continuous, I know that the domain is always going to be negative infinity to infinity. The range, since it's essentially like a line, right? All the y values are accounted for, so that would be negative infinity to infinity as well. All right, next one, we notice that this is an even degree polynomial with a negative leading coefficient. So we're going to relate that to a quadratic, remember? And we know that a quadratic that has a negative leading coefficient is going to face down, yes? Right? Again, the reason we dotted these or dashed this is because if it's a polynomial, it's going to be different in the middle than a quadratic, but the end behaviors or the ends of the graph are still going to be the same. So let's talk about those end behaviors. As x gets farther and farther in the positive direction or gets bigger and bigger, where's my y value going? It's going down. So as x approaches positive infinity, my y value is approaching negative infinity. As my x gets farther and farther negative or gets smaller and smaller, where's my y value going? It's going down as well. So as x goes towards negative infinity, my y value goes towards negative infinity as well. Again, and you know that if it's an even degree polynomial, both ends are going to be going in the same direction. And if you look here, are both ends going in the same direction? You're darn tootin' they are. All right, next thing we got to find is the domain and range. Okay, so the domain, again, should be relatively easy. Since I know that a polynomial is a continuous function, that means for all x values, the function is defined, so that's negative infinity to infinity. The problem that we run into with an even degree polynomial is the range. Because if you think about a parabola has like a max or a min point. Do you guys agree with me there? Right? Okay, the same thing is going to happen with an even degree polynomial. Okay, there will be a max or a min, so you will need your calculator. So you would plug this into your calculator and then find the max or the min. Again, if you don't remember how to do that from your previous math classes, please jump on the teacher support hour or during class, and I will be more than happy to help you find the max or min point on your calculator. But this right here happens to be the maximum. Again, it's a maximum because it's a negative leading coefficient. I'm looking for the range, so the range would be from 0.604, again, it's a bracket, right, because 0.604 is included in the range, to negative infinity. And the reason I know it's negative infinity is because both ends are going down since it is a negative leading coefficient. All right, real zeros. Remember, zeros are where the graph crosses or touches the x-axis. Again, zeros, another name for zeros is x-intercepts. So it says an odd degree function has an odd number of real zeros. An even degree function has an even number of zeros. All right, so first example here. This is obviously an example of a polynomial. Hopefully, based on the end behavior, you guys know that this has to be an odd degree function. And the reason it has to be an odd degree function is because the right end is going in a positive direction. The left end is going in a negative direction. Remember, if I were to draw a line like a linear function, this line right here in red is a positively sloped line, right? So I know that the right end goes up, the left end goes down. I know this is an odd degree function that has a positive leading coefficient. All right, so it says, remember, the zeros are where the graph crosses or touches the x-axis. Okay, so a couple things here. A couple things that we got to make sure we know and understand about polynomials. Because we had talked about end behavior relating that to a line, we said that the inside, right, not just the end behavior where the graph finishes, the inside of the polynomial is what changes, correct? So although the ends are the same, like a line, it's not actually a line, correct? There's a bunch of, looks like an EKG machine, yes? okay? And that's what happens inside of a polynomial, okay? So we know it's an odd degree. We don't necessarily know which odd number it is, right? Could it be 3, 5, 7, 9, whatever the case may be, okay? Well, here's how you can tell, okay? So an odd degree, in order to find the degree of a function, you have to look at how many different intervals of increasing or decreasing there are. Does that make sense? So what that means, based on the key characteristics that we've talked about, what's that mean is right here is a positive or an increasing interval, correct? The y value is going up, so that's 1, yes? Here is a decreasing interval. The y value is going down, correct? Okay, so this would be the second interval. Lastly, I have another interval that is going up. This would be a positive interval, correct? So I have 3 different intervals of increasing or decreasing. Therefore, the degree is 3. And that should make sense because I know it's an odd degree based on the end behavior, right? The end behavior, they're going in opposite directions, and they're going in the directions that would be a positively sloped line. Therefore, I know the leading coefficient would be positive, correct? Okay, so real quick, end behavior. As the x value is getting positive, what's happening to the y? It's going up. So as x approaches infinity, my y value is approaching infinity. As x is getting smaller and smaller and smaller, or in the negative direction, my y value is going down. Therefore, as x goes to negative infinity, my y value is going to negative infinity as well. As for the zeros, remember the zeros are the x-intercepts. So I have 1, 0. Let me erase some of this so I can actually see what the zeros are. Okay, so another name for zeros is x-intercepts. I have a 0 here. So that 0 would be at what? 1, 2, 3. So that's at negative 3, comma 0. This 0 looks like it's close to negative 1, but not quite. So we'll say it's at negative 0.8, comma 0. And the last one right here looks like it's at 1, 2. Looks like it's at 2.2, comma 0. Okay, so if we look here, we know that the degree tells us the total number of zeros. So please write that in. This is the total number of zeros. Okay, that's real or imaginary. Okay, does that make sense? Okay, and in this case, all of the zeros are real because I know the degree is 3 based on the intervals of increasing and decreasing, and I also know that I have 3 different x-intercepts, okay? As far as the domain goes, that's negative infinity to infinity, and the range would be negative infinity to infinity as well. Okay, let's look at example number 2. If I notice here, both of my ends are going in the same direction, which should be an indication to me that I have an even degreed polynomial, okay? Because again, we're relating it to a quadratic. And since we're relating it to a quadratic, both of my ends are going down. Therefore, I know that my leading coefficient would be negative, yes? Okay, now the real question is, how in the world do I find out what my degree is? Remember, we said the degree, or how I find the degree of a polynomial, is by looking at the number of different interval changes, right? Or the number of increasing and decreasing intervals, the total. So in this case, this would be a increasing interval. So that's 1, right? The y is going up if I'm going left to right. That's going down. So that'd be my second. That'd be a negative or a decreasing interval, right? Okay. The y value is going up, so this would be 3, right? And then the y value is going down here, so this would be the fourth. Can't really see that, sorry, but that would be the 4th interval. So I have 1, 2, 3, 4 different intervals of increasing and decreasing. So my degree here would be 4. Okay, and that should make sense because both ends are going in the same direction. Therefore, I know it's an even degree polynomial. I know that it's an even degree, or that it is 4, because it has 4 different intervals of increasing and decreasing. As far as end behavior goes, as the x gets bigger or moves towards negative infinity, my y value is going down. So that's as x approaches positive infinity, y is approaching negative infinity. Other side, as x is getting smaller and smaller and smaller, my y value is going down as well. So as x approaches negative infinity, my y value approaches negative infinity. As for the zeros, the number of x-intercepts. Now, I could write them in, but I'm just going to talk to you about, because this is a little bit different of a case, right? We said that the degree tells us the total number of zeros, right? Okay. Well, in this case, I'm still going to have 4 zeros, but let's classify, in this particular example, let's classify them. How many different real zeros do I have? Well, I have 2 real zeros because the graph crosses the x-axis twice, right? So I would have 2 real zeros. Okay, but I have 4 total zeros though. So since it only crosses the x-axis twice, how many imaginary zeros do I have? 2. Okay, 2 imaginary zeros. And 2 plus 2 gives you 4, right? Okay, so the degree tells you the total number. It doesn't tell you how many real zeros there are. Does that make sense? Okay, all right, so you could have real or imaginary zeros. As for the domain, again, it's a continuous function, so the domain would be negative infinity to infinity. The range would be what? Looks like it would be... What would it be? The y value here is 1, 2, 3, 4. So it looks like it would be from negative infinity to 4. And the reason I paused there is because I realized I made a mistake at the in a previous example. Remember, you're always going from smallest to biggest. So the one in the previous example up here, let me change this real quick. Right here, so this guy right here, that is wrong. It should be negative infinity to 0.604 with a bracket, right? Because we're always going from the negative, or sorry, from the farthest, the smallest to the biggest. All right, real quick. It says, sketch the graph of the polynomial function with the following characteristics. It says an odd function with zeros at negative 3, 2, and 4 with a positive leading coefficient. Okay, so it says an odd function with zeros at negative 3, 2, and 4. Well, since I have negative 3, 2, and 4, those are 3 zeros, right? And if I have 3 zeros, that means it's going to cross the x-axis 3 different times. So I could have an odd degree function with a degree of 3, correct? Right? I think that would probably be the easiest. Now, this isn't the only answer here, okay? But if you want to check with me, if you have something else you want to potentially write in here, you're more than welcome to check with me, okay? It also says an odd degree function with a positive leading coefficient. So if it's an odd degree with a positive leading coefficient, you're thinking about a line that has a positive slope. Well, if it's a line with a positive slope, I would strongly encourage you guys to lightly draw in a line with a positive slope, okay? So I lightly drew in a line with a positive slope. Well, what do I know about the ends? So this end has to be here, so the left end has to be down, the right end has to be up, okay? So then I would erase everything else in between. Okay, that's how I know I have to finish. So that means I have to start down here in the left end, correct? Okay, let me change this to red here, okay? So I know I have to start down here at the left end, okay? And my graph has to go through negative 3, okay? And it also has to go through 2. So it's got to make a bend, come down through 2, and then it has to go back up and finish where we started, right here. Okay? And if we look here, this has a degree of 3 or an odd degree because it has one interval of increasing. It has a second interval, and this interval happens to be decreasing. And then it has a third interval, and this interval happens to be increasing. Okay, so that would be an odd degree function with a positive leading coefficient. Okay, so if I had to give you the SparkNotes version, the first thing I would do here, guys, is I would probably write down the ends of my graph. Put those on there first before I did anything else. Okay, and then after I did that, I would plot my x-intercepts and go from there. Okay, all right, let's do one more. Okay, an even degree function with zeros at -3, -1, 1, and 3 with a negative leading coefficient. Okay, so you know if it's an even degree function, you are relating it to a quadratic, right? Because that's the most common even degree function you've dealt with throughout your math career. And since it's the negative leading coefficient, you know that your quadratic is going to be facing down, right? So both of my ends are going to be facing down, and then I would erase everything else in between. Okay? All right, next, I'm going to plot my x-intercepts. Okay, of -3, -1, 1, and 3. Okay. And again, this isn't the only one. Okay. So if you have one that you think is correct and you want to check with me, you're more than welcome to do so. Okay, so I know I'm going to start here in the bottom left corner based on what I know about a quadratic. My my polynomial is going to go through -3. Okay, it's got to come back down through -1, go back up through 1, and come back down through 3, and then it finishes where we had just talked about a quadratic, right? Both ends finish down. Again, I know it's an even degree polynomial because I have a decreasing interval here at 1. I have an increasing interval here. I have an increasing interval. The increasing interval was blue, sorry. The decreasing interval here was in green. Increasing interval here was in blue. And decreasing interval in green. That makes 4 total, which means the degree of my polynomial would be 4.